Okay. So let's continue the discussion of the Hopf algebra structure. Hopf algebra structure on our Yangian. So I recall the Hopf algebra structure assumes that we have an algebra H, some algebra, say of a complex number. So we have the multiplication map. The co-multiplication map in the reverse direction. And next we have some unit map, which is an embedding H and some in reverse arrow, which is called co-unit. And the antipode, which is an anti-homomorphism of our algebra. There are some natural axioms which relate all this data. The main axiom, is that the co-multiplication is an algebra homomorphism. And the key example, I repeat, key example is that of a group algebra. H is the group algebra of a finite group. G is a finite group. And the multiplication is in general non-commutative, but the co-multiplication is commutative. It's commutative, and determined by the inclusion, a diagonal map, diagonal map G to the product of two copies, which induces the algebromorphism of these objects, and this is, in the case of a finite group, this is the tensor product. And the antipode is induced by the inversion, which is an anti-homomorphism of a group itself, and hence the anti-homomorphism of a group algebra 2. And in this example, we have a squared antipode, is the identity map for trivial reasons. And now we discuss the case, the case of the Yangian, which is also non-commutative algebra. And what is the antipode? So the antipode, the definition is as follows. In the matrix notation, it's defined as follows. So what this means? This means the following thing. Let's denote this as follows. So this is a matrix valued generating series. So we have by definition, if we apply to this object, this is by definition the matrix entries. Some questions maybe, which we write as follows. So in more details, our generators, the generators of our algebra, and if we want to define an anti-homomorphism, it's enough to define it on the generators, and by definition, it goes as follows. And what are these objects? So these are coefficients of this generating series, and this generating series comes from this matrix, and this matrix is this one. So this is the definition, but we need to check its correctness. So we need some claim. Definition is correct. So what this means, that this definition should be consistent with the defining relations, because it's not sufficient to prescribe the values on generators. This prescription must be compatible with a defining relation in order to get an anti-homomorphism. So the idea of proof is to use, as usual, our fundamental RTT relation.
Сейчас, мы что-то такое обсуждали, да, по сути, вот там только было t от минус в минус первый, это был тогда прям настоящий автоморфизм, да?
Да. Здесь анти. Здесь тут немножечко все похитрее, капельку. Сейчас увидим, почему хитрее, почему я вообще затеваю этот разговор. В чем состоит хитрость? Ну, the idea of proof is as follows. So the RTT is this one. I repeat it again and again. And it can be rewritten as follows. This is absolutely trivial. Simply by taking the inverses of the matrices and okay, so this is absolutely trivial. So what is trivial? The trivial fact is this relation is equivalent to this one, which I want to finish. A little bit not evident is to show that such a relation is equivalent to the fact that we have an anti-homomorphism. So the exercise is to show that this equation just means that our definition is correct, so that is anti-homomorphism. This requires a little work. So I propose to check it. So check this in detail on the level of at least of this generating series. What is interesting? The interesting fact is that a square is not identity. At first glance, this could seem as strange, because the map, such a map, the inversion map, this inversion map, as a map, seems to be involutive. We take the inverse, take inverse again, and this should be the identity map, but it's not correct. It's not correct. And I want to explain why this is not correct and why the squared antipode is not the identity map. So first, let us write in more detail what happens. So let's examine what happens in more detail. What is S? Let's examine this map. So what we have? So by definition, these are the image of our generators. So write again. We take the inverse and take the matrix entries. And how to understand? One can write in more detail. Write this as follows. So I want to expand. So what I want to do, I want to expand our matrix as a matrix valued power series. So the entries of this object are our Tij generators of the suitable degrees. So we take the inverse of this matrix, and after that we take, maybe more pedantically, we take the Ij entries. And let's rewrite this in more detail. What we get? We have to take the inverse. So we have to invert this matrix. Invert this matrix. And how to do? Okay, so this is pretty obvious. So I write it as follows: the summation of this upper index So I want to take the expansion with respect to the obvious fact that we have 1 minus x plus x squared minus x. So I use this formula, and then I get follows and one more sum taken on the partition of M into K summons. So all MIs are integers which starts from 1. And finally, what we have to multiply the matrices and finally take the IJ entry. Let's write again. It follows. Maybe some questions at this moment? Then please ask. No? Okay, so now we have the following. So extracting the coefficient, the generator, the image of a generator with the prescribed upper index M, it gives us the following expressions on plus minus sign. Now this summation disappears, M is fixed now. So we have only some double summation. But no, sorry, we have to multiply the matrices. And by multiplying the matrices, we get one more sum. I hope it's correct. And so I want to write in detail what is this matrix entry, and because there is a product, I want to expand this product. And then we get T. Okay. So we get a rather complicated expression. See? Rather complicated expression, which already explains that this operation, the antipode, is not so trivial. And in particular, some simplest cases. So what we have, so first of all, from this we have Tij1 hat. Okay, this is, I'm sorry, minus. Okay, this is more or less evident. And I want to compute the next example, and this is as follows. Plus and plus the sum A and A. So what we have is examples. So what is the conclusion?
Sorry.
Сейчас там последний индекс 2 или 1?
Oh, thank you. Thank you. I'm very sorry, because it's as follows.
А почему там минус в первом слагаемом?
Почему минус первым слагаемым? Минус первым слагаемым. Может быть, это и не так. Может быть, это и не так. И таки не так. И таки не так. Я думаю, что, наверное, вот так. Я думаю, что вот так, наверное. Да. Да. This is because, thank you. This is because K is responsible to the power in this formula. We write it as if follows.
Сейчас сказалось, что степень при U должна быть равна сумме степеней в T, как бы, ну не степеней, но вот номеров этих M и их.
Ба-ба-ба-ба-ба, ба-ба-ба, ба-ба-ба. Ну, наверное.
Может быть, там U в степени M, а вот...
Да, наверное, это надо... Вот так надо. Наверное, это надо разделить. U в степени минус M. Минус M. Минус единица в степени K. Вот тогда хорошо будет. Тогда, наверное, будет хорошо.
Ну да, потому что когда мы геометрическую прогрессию раскрываем, у нас вот K будет, это как бы степень вот этого остатка от ну, того, что не единица.
Да, спасибо. Да, это я напутал. Это я напутал. Это я напутал. А здесь уже U никакого нету. Тогда, значит, здесь будет... Нет, это тоже здесь не нужно. Тогда нужно ставить минус единицу в степени K. Так тогда, да? Вроде так, да? Вроде так. То есть сначала мы смотрим, какая степень, это k, потом мы извлекаем коэффициент, отвечающий u в степени минус n. Тогда у нас получается вторая сумма. Это вот вторая сумма. Ну и для того, чтобы набрать вот это m, мы должны взять произведение. Вроде так. Есть ли какие-нибудь еще замечания? Может, мне еще это надо уличить в чем-нибудь? Я напутал. Ну, будем надеяться, что все правильно. Ну, тогда вот, so we have these formulas. And I want to show, I want to check that. So check that already on this level we get something different. And indeed, what we get. So we apply. So we have applying the antipode, we get this expression. And next we have to apply the antipode twice. Applying twice, we apply first to this. Oh, sorry, I don't want to. So this gives us minus this sum so again I'm sorry. So I simply applied the antipode to this expression.
Сейчас, а там, это же антигомоморфизм, там не нужно поменять порядок.
Нет, пока не нужно. Это я пока воздействовал S на вот эту штуку.
А, хорошо.
То есть это...
Да. Из-за этого как раз и проблема, я понял.
Да, из-за этого-то и будет проблема. Вот теперь мы должны, but now we have to apply the S to this expression. And we get what we get. We get this. If these letters are commuting, then there is a consolation. But in our situation, they are not commuting. So we get some rest term, which is easy to calculate by taking the commutation, by using the commutation relation, which is the same as the commutation relations for the matrix units. And so we get something different. We get this, some partial cancellation, and some rest term, which shows that the S squared is not identical. And a more detailed analysis shows that the following theorem, I don't want to prove it just now. So we have a theorem without proof. I want only to state the result as follows. Actually, in matrix term, if we apply the square antipodes, this should be some algebra automorphisms. And these automorphisms looks as follows. Let me first write it and then explain the meaning. So what happens? This, so this is something I don't want to write. So S2 is an automorphisms. It is the composition of two automorphisms. One is the shift of the argument. And because the RTT relation is stable with respect to shifts, we already discussed this. This is correctly defined automorphisms. And next we have multiplication, but something which is central. And the idea is that if you look at the RTT is equal to this relation is not affected. The validity of this relation is not affected if we multiply the T matrix, but something which is in the center. Because this amounts by multiplying the two sides of our relation by this. We can regard this just as a scalar. It's not a scalar, it's not an element of a base field, but it is a scalar in the sense that it does not affect the multiplication, because this is a center. Okay. So we get some non-trivial automorphism, and even more, we see that as an element of this group has infinite order. So the situation is, in this aspect, is quite non-trivial. Not only the antipode does not look as the usual inversion map, but its iteration gives us an infinite cyclic group. But this does not contradict the axioms of a Hopf algebra. It may happen, well, that the squared antipode is not equal to identity. Okay, what next? Let me recall now the definition of the co-multiplication. Sorry. Co-multiplication map is definition in terms of the generated series. I call it as follows. You see, here there is some evident analogy with the matrix multiplication. I'm sorry. Which means, if you want to see what happens on the level of generators, simply we have to expand both sides as generation series, and we get formulas for generators. And in matrix form, I recall, it can be written as follows. And what is this? So this is an element of this algebra. I recall that V is our coordinate space. To simplify the notation, I omit the formal parameter, which is implicitly contained. So more precisely, we have to include these parameters inside this object, but let me omit this. So what we have, our convention is that if you take, in general, we are dealing with some product of some copies of the Yangians and times also some copies of this end space. And the indices in brackets refer to the copies in this product of the Yangians. And the second index which will appear corresponds to copies of this object. So in this notation is as follows. So here there is no, this sign is omitted because it is implicitly contained, it is implicit in this notation. So this is a good notation because it enables us to manipulate with the RTT relation. So as an example, let me prove a proposition which says the follows. If we apply the coproduct to our quantum determinant, we simply get this sense, as I already mentioned previously, the quantum determinant can be viewed a little bit non-rigorously, but as a group-like element in the Hopf algebra. Of course, it's not an element of the Hopf algebra, it's a generating series. But nevertheless, it's quite correctly to say this is a group-like. So how to prove this? The idea is to rewrite this as follows, using the same type of notation, but without the tensor product symbol. Let's use this notation, and we see that it is pretty easy to show. So what is the proof? So the proof goes as follows. So we are working in such a setup. 2 copies of the Yangian, and we need n copies. Of course, this is the same as the endomorphism of the n-fold tensor product of our auxiliary space V. So we want to make some manipulation in this huge space, and the reason is because the quantum determinant is defined in terms of this object. So this is why we want to use it. And I recall definition of quantum determinant. It is based on some non-trivial relation. So I recall that this is the normalized anti-symmetrizer in the group algebra of a symmetric group. And R, its image in this big endomorphism space. So simply the permutation group acts by permuting the copies. And so we get, and let me denote it to simplify the notation as follows. And with this notation, we have the following. Take the product. N times and this is equal, actually, we proved this is equal to this. And I recall that this symbol denotes some one-dimensional projection operator in this space. So we get this one-dimensional projection operator times some element of a Yangian, which is not exactly the element, but generating series which is central, and this is our quantum determinant. But what is also important, that there is an alternative expression of the same object. Namely, we have to rewrite this as follows in the reverse order, and to use this. And now we play as follows. Now using this, we apply, roughly speaking, we simply apply our coproduct to this relation. So first we do, so apply, apply. First, let's do, we apply to this term. So,
Можно вопрос?
да.
А там вот в Т1 должен быть, в самом нижнем равенстве, в Т1 должен быть такой параметр? То есть мне казалось, что параметры с номерами должны быть как закреплены. То есть что у нас в Т1 всегда U, а в Тн всегда U минус n плюс 1. Ну, может, я неправильно запомнил.
Нет, мне кажется, что там вот так.
Там
вот,
ну, хорошо, понятно. Спасибо.
Мне кажется, что так. Надеюсь, что так. Так, okay, so we apply the co-multiplication to this and show what we get. So by the very definition, we get because the co-multiplication does not affect this object. It is applied only to the Yangian terms and not to the endomorphisms of our space, so it's correct. But next, look at this first. So what we get after applying the co-multiplication, each terms should be written twice. More precisely, what we get, on the left we have this. But now we have to write something like раздваивается эта матрица. Next we have okay. But now the key observation is that two metrics. Commute for I distinct from J. I already used this observation, and let's use it again. And using it, we easily see using it, we can write as follows. First, we have this projection. Next, we have only operator with a bracket index 1. And next we have, next we have so this is the first collection, this is the second collection. Okay. But now we apply our relation, which gives us the possibility to rewrite such a product as such a product. So this enables us to move this projection on the right. But we have this, it does not matter. So we apply, and so we get something as follows. I don't want to already to write. And we have a second product. So that first product, the second product, first and second. Okay. But what is this? But this is by definition this object. But now we can, using this, we look at this object and do the same. And so we move on the right by rearranging this product. But now we get, and then we get what we want exactly. And that's all. This is the end of the proof because it shows that we start with this and we arrive to this. So we have again projection, our projection operator multiplied by something. And this something is what we want exactly. So we need these projection operators because it is necessary to apply our initial definition. This is more, it's a little bit tricky, but it's better to do than if you write the quantum determinant as the sum of permutations plus minus. It's better to do. Okay, so this is demonstration. Again, is demonstrate the effectiveness of the RTT formalism. Maybe some questions or remarks? Okay. Well, so what I want to do next. The next is only some remark. So let me recall that is a deformation of the universal enveloping algebra. We take the polynomial currently algebra, GLN, polynomial functions with values in our GLN matrix Lie algebras. So the algebra of functions taking values in the Lie algebra. This is a deformation. In the sense, this can be explained by using some deformation parameter, but at the moment, let's say that this is a filtered deformation, meaning that we have some filtration, the second filtration in my terminology, the filtration in the Yangian, which is determined by proclaiming that the second type degree of generator is by definition not m by m minus 1, assuming that because if m is equal to 0, this is simply the constant, the Kronecker symbol, so we don't need to take m is equal to 0. So this is very important. This is a very minor fact, but the whole idea is based on the fact that we have this definition, and for m equal to 0, we should take minus 1, but we don't need to do this because this is a scalar. So this is the basis of the argument. And so the fact which I use is that we have taken the graded algebra associated to this filtered algebra. It's isomorphic to this universal enveloping algebra. Now I want to simply notice that this claim also extends to the Hopf algebra structure. So this fact extends to the Hopf algebra level. So this means that this isomorphism is also an isomorphism of Hopf algebra. We have a Hopf structure here. This Hopf structure is compatible with the filtration, so it descends to the graded level. And this is also a Hopf algebra because any universal enveloping algebra is a Hopf algebra. So this is quite a general fact. General fact is that for any Lie algebra is a Hopf algebra, which is co-commutative. The coproduct is defined on the level of the generators, that is the generators, the elements of Lie algebras, as follows. X, the Lie algebra. This is commutative. but here the co-multiplication is not commutative. How to see that after, if you descend to the level of the graded objects, this non-commutativity disappears. This is easy to see. Indeed, what we have. We have to look more in detail on the co-multiplication when applied to our generators, what we get. It can be, we have to write our initial definition in terms of the generating series and then extract the coefficients on the left and on the right. And if you do this, you get the following. You get first of all, we get this. But then we also have some additional terms, summation from R to 1 to M minus 1. Sorry. Okay. We have to I hope it's correct. And what do we get? On the left, degree is equal to M minus 1. The degree is preserved under the co-multiplication. This expression also has M minus 1. But this term is degree is equal to R minus 1. And don't forget that R starts from 1. And also it ends with M minus 1. So the degree of this object is equal to M minus R minus 1. So the total degree is M minus 2. So actually, these terms disappear when we pass to the graded algebra. In this sense, we see that the Hopf structure after this procedure, meaning we look at this picture, it becomes commutative because we get this which exactly corresponds to, which is similar to this. I recall that these elements, it's also, I want also to observe, it is also important, that under our procedure, it turns, which is an element of a Lie algebra. So this becomes an element of a Lie algebra, not of a universal undeveloped algebra more generally, but these are simply elements of a Lie algebra. So this picture is quite similar to this one. And likewise for the antipode. And again, the same little argument shows that modulo some low degree terms, the antipode is the usual antipode of the universal undeveloped algebra, which is very simple. The universal undeveloping algebra antipode is x goes to minus x. And that's all. Okay. Some questions maybe? No? Please ask. Don't hesitate. Okay. But now I want to give some application. Of co-product. So new proof of Poincaré-Bergov-Witt. The idea is due to Brandon Klishov. There are papers in communications, mathematical physics. This paper contains some material, some quite non-trivial material, but it contains also another proof of the Poincaré-Bergov-Witt. So what we want to prove? I recall the general formulation that we can choose an arbitrary total, that is linear order on our generators. And then the claim is that if you take ordered monomials in our generators, then they constitute a basis. The fact that the linear span is the whole algebra, it's trivial, but the non-trivial part is that the ordered monomials are linearly independent. So this can be stated in the following form. Theorem, Poincaré-Bergov-Witt type theorem for Yangian is as follows. So let's fix some natural L and a total order on the finitely many elements Tijm with, these are our usual restrictions, and we also want to restrict M. It's enough for the proof. Then the monomials are linearly independent. So this is Poincaré-Bergov-Witt, and I want to explain how to prove this in a different way, using the coproduct. Proof goes as follows. Let me recall that we have a truncation homomorphism, algebra homomorphism. which is defined as follows. On the first level generators, we get the matrix units, and the remaining generators are killed. And we use this homomorphism combined with the iteration of our coproduct. And the idea is to reduce all claims to the level of universal enveloping algebras, to the Poincaré-Bergov fit, but for the universal enveloping. So we also denote some iteration of coproduct, which is defined as follows. The usual structure is always. But formally, this means that we take the usual product, the usual coproduct corresponds to L equal to 2. So we have, first we have this, then we apply the coproduct to some copy, say to this one, then we get triple tensor product. And we can do this in any way because the result does not depend. And we exactly get this expression. And what is important, that it is an algebra morphism. So we say that is an algebra morphism. And combine it with that is, we apply psi to each copies. So we get the combined map, which goes first to these copies and next to so we get the composition, which is an algebra homomorphism. And we want to prove that our ordered monomials are already linearly independent in this object, in this algebra. And this will apply our claim, of course. So our goal is to prove this claim. So let's compute what happens. And we use the fact that our truncation is quite a simple object because it kills all higher generators. And using this, we get so let's write in detail our map. Our map means this one. Since to what? To the sum and next we have to extract the coefficients in our generating series. We have a L-fold product. This corresponds to this partition into L summons. And we get so what I wrote. And next we have to apply on this step. I wrote this line corresponds simply to this intermediate step. But next we have to apply this arrow. But when we apply this arrow, some terms are killed, because if one index, upper index is at least 2, it is killed. So after application of this, what we get? Only terms with equal 0 or 1 contribute. And the remaining terms are killed. And this shows, it follows, that actually we get the following. False is given by the following expression. We have to look at the positions where the upper indices are equal to 1. This is reflected in this summation. We have to specify m positions, exactly m, because we must have m summands equal to 1, and the remaining summands should be equal to 0. Okay. And next we have again the summation over these indices. I'm sorry, not m. But this one. And this becomes clear after I explain my notation. After explanation of a notation. What is my notation? My notation is with ij n, sorry. Is by definition the ij matrix unit in the art copy G, because U of G of N is the same as universal unavailable algebra as the direct sum of L copies of G of N. So we take some copy number R and the matrix unit in that copy. So this is easily to see from the very definition. From the very definition, if you look at this product and remark that when the upper index is equal to 0, then it should be the Kronecker delta. And if it is equal to 1, it is a matrix unit in the corresponding copy. And these Kronecker deltas are just the reason why the L copies here, the L summons here, turned into M summons here. This does not contradict to the fact that we have only M-1 indices A and not L-1 indices. This is not, this should be understood. It's easy to see because some deltas, if you have something like this simply shows that 2A indices are the same, should be the same. And so there remains only M-1, a smaller number of independent indices in this summation. So we have this. We have this relation. Are there questions about this? No? Okay. So let me So let's play with this expression now. So what we want to prove? We want to prove that the ordered monomials in these expressions are linear independent. This looks a bit complicated, but it's not. Actually, it is not. So the claim is as follows. The ordered monomials composed from ends of type are linearly independent as elements of this algebra, this universal unavailable algebra. So now a reduction number 1, but actually it's enough to prove it's sufficient to prove the same claim but not in the universal enveloping algebra, but in the symmetric algebra. Using some obvious argument related to the filtration and the associated graded algebra. And now we don't carry about don't care about the order, because we arrive now to a commutative algebra, and the order does not matter. Reduction number 2. Reduction number 2. Look, what is this? The symmetric algebra on a finite dimensional space is the same as the algebra of polynomials on the dual space. But in this situation, we have a fixed basis. So this is again a direct sum of L copies of metric spaces. So we can fit the same, reduce the same holds, we claim, the same holds in the algebra of polynomials. In what? In L matrix variables. Say A1, AL, which range over the space of matrices. And in this notation, maybe it's better to say in this interpretation, these elements as polynomials are polynomial functions of the following type. Have a triple index I, J, and M, and given such a triple, we have a polynomial function in L matrix variables, but looking at what is written here, we see that this is the same as taking the following. The summation over the R variables, and the summation of the A indices disappears. We simply pick our arguments which corresponds to these positions, multiply the matrices, and then we can take the IJ matrix value. After multiplication, we get a single matrix, and we take the IJ matrix. So we have such a function, which strongly resembles to the elementary symmetric polynomials. Only the difference is that we apply the same definition, not to commuting variables, but to non-commutative and matrix variables. But formally, it looks quite similarly. And now we argue as follows. We consider a polynomial map. Of the multi-matrix space, which I mean that we have a space of matrices, the direct product of L copies. This is a multi-matrix space, let's call it as follows. And we want to consider some analytic, even polynomial map of this space into itself, which goes as follows. We start with an L tuple of our variables, and it is mapped to another L tuple of matrix variables, where Bm is by definition the sum as above. It's a polynomial map, and reduction number 3 is the reduction to the following claim. The matrix where is above. Sorry, I want to finish. I'm a little bit late, and as functions on our space, multi-matrix space, are algebraically independent. If we prove this, we get our claim that monomials are linearly independent. And the next reduction is as follows. So we have some analytic map, polynomial, but it's sufficient for us to have an analytic, complex analytic map of our space, which is actually a linear space. So our multi-matrix space is a linear space. Our space is actually linear space of dimension n to raised to the power 2 by L. So this is the number of coordinates. The matrix values are coordinates. And because this is a good map, it's enough to show that the differential in the space, in the sense of different geometry, a linear space is mapped into another linear space, and we get the tangent map at a point. A differential at a certain point is non-degenerate. If we prove this, it's enough, because we have some change of coordinates. We have initial coordinates, and at some point, the images are, the tangent map is 1-to-1. So the image of these coordinates gives us, again, an algebraically independent system. So we want to prove this. at a certain point. And what is the point? And if it's true true also almost everywhere. But it's enough for us to exhibit a single point. So we take a special point, which is as follows, which consists of scalar matrices. Some scalar matrices, and these are complex numbers which are pairwise distinct. And I want to prove that the differential, I want to compute it. It's not degenerate. But what is the differential? The tangent map. At this point. The Jacobian. We want to compute the Jacobian. So what we need to do, we take one set of coordinates in the image. And our initial coordinates, which corresponds to this. This may be bad notation. Sorry, maybe it's better to write as follows. It's not difficult to see that this is equal to 0 if this by index is distinct from this by index. So actually, all this picture splits and becomes one-dimensional in a sense. And it is equal to the only thing that we have to analyze, so fix I, J, and assume that M and R both range from 1 to N. So actually, we are left with L variables. And the idea is that what happens? The idea is that this derivative, is simply the elementary symmetric polynomial in these variables with the R variable excluded. Is excluded. The head means that this variable should be excluded. And so the final reduction is as follows. The determinant, the L by L determinant, which is composed from the elementary symmetric polynomials with this variable excluded. Here M, R ranges from 1 to N. So example, to give the situation more. So we in this case assume that L is equal to 3. Then what we have? M is equal to 1, then M minus 1 is 0, and we have ones, because the index 0 elementary symmetric polynomial is the scalar 1. Here we have to exclude the first variable, so we get, and likewise we have and finally, we have the elementary symmetric polynomial of degree 2, the same variables, but multiplied. And this is easily computed. This is the van der Monde. And more generally, this is an exercise. This determinant is equal to the van der Monde. And because we assumed that the pair was distinct, the van der Monde is non-zero. This explains why the tangent map is non-degenerate. This is a nice exercise on symmetric functions. So this is the end for today. Let me switch off.